slides again. And this last 1 hour lecture is about interference.
I realised talking to a number of people, mainly in the club last night, that some aspects of master equations were known to some of you in great detail, but others less so. So I put in some extra slides on Paul Markov and the master equations. Those of you who've seen these things many times before, well, you get reassured that it's something you know all about. You can doze off at that point. Okay, so just to remind you about these things, I've taken some slides from my friend Professor to add in on this. If you take a completely closed system, some sort of impermeable barrier, then what you get is unitary dynamics. The rest of the universe is just decoupled out there and doesn't play any role in it, and you just solve the Schrödinger equation under various sorts of ways. And you get unitary evolution, totally reversible. This is how quantum mechanics was actually set up. But that's not the way the world is, and it's not the way that the world is interesting for us, because you've always got this environment around, and the environment interacts with the system. So you've got this openness that sometimes you could regard as dissipative. You get a decay of systems. And what I'm going to try and distinguish today is dephasing, dissipation, and decoherence, because they're very different things. And we'll see how it works. So you've got this rest of the universe, and I'm going to label the environment with this script, capital E, all the time. So what I'm going to do is just run through the beginnings of how you actually deal with this open system. Now sometimes the external interactions, it could be a perfectly classical sort of fluctuating thing, or it could be a quantum mechanical thing. In David's lecture just now, he talked about some of the surface interactions, where you get randomly fluctuating influences on phase, and I'll talk about some of those as well. And in other places, you're actually losing information out to the environment. The trace operation, where you looked at just the internal density operator of the system you're interested in, you trace out the rest of the environment, you lose information. And the irreversibility that comes from that trace operation is also of interest. We'll explore that. Okay. So, just to remind ourselves, imagine a two-level atom. And the two-level atom, we're going to drive with a sequence of pulses. If these pulses are actually pi pulses, let's just do a bit flip. So that a superposition like that becomes a superposition like that. Then you've got a unitary operator, and all that's happening is that sigma x is acting on your superposition in that particular way. And that's a simple train of these bit flips. And you could have an nth realization of this, where the pulse is arriving at N1, N2, N3, and so on. And if the arrival times of these things, if they're randomly arriving, you get this stochastic process, and if I average over it, I'll get some sort of probability distribution of these arrivals. So you can see randomly flipping things of that kind would be an example of what would happen if either you're not really controlling how the pulses arrive, or it could be an idealized model of what's going on with little surface interactions. Okay. Right, so the problem is you've got this incredible fragility of superpositions. You get this coherent superposition. Wow.
Too fragile.
Much too fragile. Yeah, he doesn't like it. Right, we'll do it bit by bit then, shall we? You've got a coherent superposition. Decoherence means that your spin up or spin down state, you end up in a statistical mixture of these things. And that's kind of things that I'm interested in, where the pure state that you started off with, that you manufactured, ends up in a statistical mixture of these kinds of things. So just to remind people about the way that you've actually got a double average going on, where you describe the density matrix. If I got some sort of Hamiltonian that I'm interested in that describes, say, an atom, then what I'll do is I'll take the expectation of this. So I've got a quantum average that's going on, but then I've got a whole set of uncertainties about how I might have prepared it. So I've also got a classical average that's going on over the PNs. So there's a double valued system that's going on. when you've got these kinds of engagements, so both the classical and the quantum one. So if you have a two-level atom, for example, you might be interested just only in the atomic properties. You do a trace operation on these things. And what we're interested in is really what's going on in the system rather than in the environment. So what often we'll look at the reduced density operator just for the system on its own. Right, so if I take that density operator, and I've got both the quantum mechanical pieces and this classical weighting and these things, then if I look at the density operator, I've got excited state probabilities in the diagonal, and off-diagonal elements are the coherences that we've been interested in. Okay, so what we've got is quantum state of the system and its prepared uncertainties that are perhaps of the quantum mechanics, and there's some classical ignorance about how we actually put it together. So if we look at that density operator, the density operator is summation, its eigenvalues are going to be greater than or equal to 0, and the trace of rho squared will be less than or equal to 1. Now, if you have a pure state, then what you do know is the trace of rho squared will be equal to 1. So that purity operation is actually, calculating that is often a good way of looking at the degree to which you've got some sort of mixed state that's going on. Okay. So let's have a spontaneous emission rather than these stochastic fluctuations. In spontaneous emission, an excited state goes down to a ground state, you get a spontaneously emitted wave packet out in the electromagnetic field on the detector. And there's an irreversibility in this, because once you've actually got that record in the photon detector, you've lost the information that may have been accessible in this combined atom environment system. The atom detection is removing that information for it. It will provide information, it will give you a click. Okay. So there's a measurement process from which you can infer what was going on in spontaneous emission. And the master equation that I was going to assume everybody knew about is this, but I'm going to go back and actually go through the origin of these various Lindblad terms that turn up in the master equation. So you have a coherent dynamics, and then you have a damping term, and in this form, which is called the Lindblad form, this is L. The Lindblad operator in spontaneous emission is a sigma minus, the lowering operator. So the way that Lindblad works, you can see here you've got a sandwich term there, and you've got this anti-commutator that sits there. Okay. So what I thought, having talked to folks in the pub yesterday, is I might actually go back a bit and explain a little bit about how those Lindblad terms derive before we start to apply it. Right, so for Markovian master equations, or not, if we go back to the way that the general systems evolved, there's a lot of people who looked at that. Lindblad is the name that's going to occur throughout the talk. Sudarshan and Kosolowski did a very formal approach in terms of maps. So if I take my initial density operator, I evolve it to time t, and there'll be some sort of map phi. And what a lot of mathematicians have done have been developing properties of what that map does. And I'm not going to go through the whole basis of that, the craft decomposition, for example. Just take that for granted. On the other hand, what quantum computations do is they make specific models of the way the system interacts with the environment. So rather than looking at the general properties of that map, they actually give you a demonstration of what that specific phi will be, the evolution operator that's relevant to that, and then evolve it. And whether or not we're going to be using a Markov approximation, which is part of that Lindblad formalism, in other words, something which involves white noise, delta correlated noise, an awful lot of what we do is we assume it's going to be Markovian. A lot of really interesting things are not Markovian, and we'll try and distinguish them. Okay. So if I've got this open system, okay, so I've got my internal system I'm interested in, I've got a reservoir, I've got a system Hamiltonian, a reservoir Hamiltonian, a coupling V, then the Liouville equation is just this, okay, but what I'm interested in is the system operator, density operator, the reduced density operator for the system, trace over the reservoir. Well, the initial state, I'm going to assume is factorizable, okay, so that my initial density operator is the reservoir operator at t equals 0, and the system operator at t equals 0. There are systems that will not be valid. in some collisional actions, in line broadening, that isn't true. It isn't factorizable at 2 equals 0. Okay, and that's very complex to analyze. But in most of what we're interested in, spontaneous emission, the way the qubits evolve, cavity QED, we'll assume that you can actually factorize that. Okay. So if I take that formal Liouville equation and I just iterate it formally like that, okay, and I trace over the reservoir, then what you can then deduce under a set of approximations is a Born-Markov master equation. Where in particular what we'll do is we'll assume that this reservoir is really big. So whatever you do to it, you don't really change it by your little quantum system engaging with that reservoir. In other words, the reservoir is so big that whatever the system does hardly affects the reservoir. Now, when Martin was just speaking earlier about his vibrating protein as a little lever, okay, it was quite clear that the qubit, the system that is in there, was actually interacting with that and changing it. But if you have a huge number of these things weakly interacting with the environment, bit by bit, then you can actually assume that the density operator is unchanged. The other thing to assume is that whatever your coupling between system and reservoir is, it's got no diagonal elements. In other words, the trace of the reservoir variable of V of t rho of r is 0. That's pretty trivial, really, because if there are diagonal elements, you can just bang them into the interaction definition of the Hamiltonian in the first place. And then you assume V is weak. And I did have a couple of conversations with folks about what V weak is, so I've inserted some extra slides about what that means. If you do that, you can end up with a Born-Markov master equation. All right, so I thought this is where we've got to insert stuff to see what weak actually means. So let's assume a little model. So a quantum optician model is always we have a bath of harmonic oscillators. And we've got this coupling between system and the harmonic oscillator bar. So there's a very large number of these harmonic oscillators and one system operator, capital A. We'll assume the environment's in thermodynamic equilibrium at t equals 0. Okay, so we've got this thermodynamic environment, and we're going to assume, as I said, no diagonal elements for V. Okay, right. So let's see if we can get that Lindblad form. The first thing to worry about is coarse graining. When you derive a Born-Markov approximation, you're going to do simultaneously a number of things. You're going to coarse grain over a time delta t. You're going to worry about short time dynamics, and you're going to worry about long time dynamics. So there's a positioning of that coarse graining between these two extremes. Okay, so what I'm going to do is evolve this density operator for a time little delta t. So I've got this funny map, which is going to take my density operator at time t and to evolve it to t plus delta t. Okay, so I've got an evolution. I'm going to trace over the environment. I'm not interested in environmental states. I've got my factorizable. There's my density operator at time t. There's the environment, which is not changed. So at time t, it's the same as it was at time t equals 0. And I've got an evolution operator, which is moving it on by this amount delta t. And the coarse graining time is going to be this coarse graining time delta t. I want to be much, much less than the decay time. You don't want to be coarse graining over a time when the system is evolving by an enormous amount. So you've got this characteristic decay time, for example, gamma to the minus 1. That could be the spontaneous emission lifetime, for example. The coarse graining is actually much, much shorter than that. Okay? And that means that V has to be weak. When I was at Sussex, Tony Leggett was my next door neighbour in the office, and he used to say, Conoptics is completely bloody useless, because all you're doing is weak coupling. Okay? Because V has to change things by a tiny amount by measuring delta t. And the sort of squid things that he was interested in, you could not make that weak coupling approximation. Okay? But in quantum optics, the sort of things that we deal with, it's almost always true that you've got this weak coupling interaction. Right. So then what I can do is to essentially try to derive a derivative. So rho of t plus delta t minus rho of t divided by delta t, you can just expand out, and then what we're going to worry about is how that coarse graining time actually works. Okay? And you can exploit the idea that the correlation time of the reservoir is really small. Okay? So what I'll do is I've tested that previous equation and I've expanded to second order. You don't need to go any further than that. And it's pretty horrible. But you can see that what you've got on the driving terms on the right hand side are correlation times. You've got V of T1, V of T2, these interactions at two different times, T1 and T2. And in almost everything we do in quantum information processing, quantum optics, these correlation functions are essentially, have got an incredibly short memory time. So the correlation functions are essentially delta functions. And if they are delta functions, then everything in here really simplifies. Now, it will approximate to this delta function if you're averaging over a broad range of energies in the environment. So you've got a very broad range delta E, which is much, much bigger than anything else you might consider. So the function, you've got a correlation time, which is Planck's constant divided by that range, delta E. And if you assume that the reservoir is very broad, that's a white noise approximation, then what will happen in here is you'll get these correlation functions being approximately delta functions. If you've never seen this before, it's beautifully explained in Kostanuji's quantum mechanics textbook, for example. There are examples where the reservoir range, delta E, isn't broad enough for that to be a delta function. If that's true, then you get non-Markovian dynamics. So one of the things that was interesting about Martin's discussion about the density of states in his biological transfer is that, is it broad or not to make that a delta function? Well, that's still an open question. Right, so let's assume it is broad. We've got this delta E, which is enormous. Okay? Then what you can do, if it's this delta correlated white noise, what you can do is all these funny driving terms that we had in that evolution equation for rho, now is a delta function. And what you can do is do all those integrations, and what you find is a damping of gamma and a shift. Okay? I'm not going to discuss that shift any further. It's a kind of prototype lab shift, basically, due to the engagement with the environment. I've swept under the carpet a whole raft of things involving, for example, rotating wave approximations here, but that doesn't matter. Okay, so if I do all of those things, what I've done is I've got my coarse graining time, that's delta t, and delta t is going to have to be longer than the correlation time of the reservoir, but short compared with the decay time. Okay, so you've got this trio of times to remember. The correlation time of the reservoir, which for spontaneous emission is essentially 0. The decay time for the system, which is going to be very long, and of course graining time in the middle. If you can do all of that lot, then what happens is that little difference equation has that sort of form. You can then start taking delta t to be pretty short. Was that me? It was, wasn't it? There. If you take that delta t to be, then you've got this differential equation, which is now the Lindbladian that I spoke of. Okay? Of course, it's slightly bogus, because I assumed that delta t was finite. It was actually bigger than that correlation time. Then I took it to 0 to get a differential. Okay? That will only really work if tau c is essentially near enough 0. Okay? But if it is, then you get that. And that's basically the Born Markov. Right. Now, when this system couples to the environment, you can trace over it, you've got this reduced operator over here, and all these, for a single inlet operator, it always looks the same. You've got a sandwich term, the rho is sandwiched between a Lindbladian and its conjugate, and then this anti-commutator. And that gives you the fact that you've lost information out there into the environment. Measurement within the environment could actually reveal that information. Okay? So what we've been interested in is the way in which you reacquire that information to see what's going on. And that's the whole basis of quantum geometry with these things. That what you actually do, increments of time by increments of time, is obtaining information in the environment, revealed by the measurement out there in the environment. That's basically an update of your density matrix. That gives you the idea of jumps. Right. So let's look at straightforward two-level atom in a cavity. The cavity is damped. There'll be a resistivity at the walls of the cavity. And look at the way the Rabi oscillations bounce up and down and see what happens for a particular realization. Okay? So you get Rabi oscillations, but every now and again, the engagement with the outer reservoir will cause a jump. Okay, a quantum jump. So you'll get this. So that's what a single trajectory looks like for Rabi oscillations interacting with the environment. It doesn't look like damped Rabi oscillations, because it isn't. You get these interrupted jumps. But if I now average over a whole sequence of these random, when those jumps have occurred, then I'll get damped Rabi oscillations for the ensemble. But for a particular realization, it'll oscillate, then it'll jump, then it'll start oscillating again, there'll be jumps. And you can ask, are these things real? And we'll start arguing about what real means and so on. Okay, so I want to give some examples of that. Oh, that's what I said, never mind. Right. Just wanted to have a quote from Schrödinger at this point, because this whole idea of jumps was very much the Göttingen school of the interpretation of quantum mechanics, and Schrödinger absolutely hated the idea. He liked the idea of continuous differential equations describing the evolution of it, and he said, sorry, I don't like it, I'm sorry, I don't have anything to do with it. He spent a long time worrying about it. Had I known that we were not going to get rid of this damn quantum jumping, I'd never involved myself in this business. Well, too bad. Right, so let's look at this business of disentangling what's going on from the bulk, looking at individual equations. So as I said, I've got this evolution equation, which is describing what's going on. There's some sort of decay, gamma, between system and environment. If it's a field mode interacting with a cavity at 0 degrees temperature, put temperature to 0, that's like really easy, then all that happens is my harmonic oscillator in the cavity decays away at the rate gamma. So the Lindbladian, acting on the density operator for the cavity field alone, has this. It's got, actually you guys have used my battery up. You've got this term, and the sandwich term, anti-commutator, the sandwich term. So if I took field damping, cavity field, with a finite Q in the cavity, the decay rate, gamma, that's relevant in this Lindbladian, is just the frequency of the cavity field divided by the Q, the quality factor of the cavity. That's the decay rate of energy. What I'm going to show you is that that's not the decoherence rate. Okay? Let's imagine that we get a situation where we make a superposition of field states separated in phase space, talking about delta alpha. Okay? So some blob of phase space over there, and another blob over there, and the separation between them in phase space is delta alpha. And what I'm going to show you is the decoherence rate, the way that superposition behaves, is given by the energy decay rate times the distance in phase space of those superpositions squared. And that's much, much faster than the energy decay rate. Okay? So superpositions are decohering in that sense much, much faster than the energy is going. Okay. That's why I want you to distinguish energy decay, that's dissipation, from superposition decay. Right. So if we're looking, just to remind you of the Wigner functions, because that's how I'm going to describe these things for fields. All I'm going to do is work out my density operator. I keep doing that. Right. Density operator, displacement operator, that gives you the characteristic function. I just take the characteristic function of Fourier transform. I've got my Wigner function in phase space. And let's have a look at some Wigner functions. So if I take a 9-photon Wigner function, so a Fock state for 9 quanta, they could be phonons in one of the trapped ions in a harmonic cavity, could be photons. And the Wigner function for a 9 excitation state is a Laguerre polynomial with this outer Bohr-Sommerfeld ring. It's out here, there's the Bohr-Sommerfeld ring. And lots of these oscillations that are going on, the category of the Laguerre polynomial for a Fock state. There's a little blip down the bottom here because it's gone negative, and the whole thing's been lifted off to tell you that it's non-classical in that sense. Right, so that's your initial Fock state with 9 excitations. Now I'm going to involve that in a cavity with a damping rate gamma. Okay? That's what happens at 1/10 of a dissipation time. Okay? That's what it was initially. 1/10 of the field damping rate time, the field damping time later, it looks like that. Okay? There's still a bit of negativity. See, it's lifted off the floor. But an awful lot of those oscillations that are going on have gone away in 1/10 of a damping time. Now, one way of seeing this is that you could actually make that Fock state out of superpositions of coherent states on a ring. Something I played with quite a long time ago. Those superpositions, you have a lot of these, you put coherent states out there on a ring. The distance between any element in that superposition is that. That distance is root n. Okay? Because the Bohr-Sommerfeld diameter here is root n. Okay? So the distance between the elements in the superposition is root n. The distance squared is therefore n. So these things are really decohering at time n gamma. Okay? Right. So at time n gamma, 1/10 of the decay time will gone away. Right. So let's look at how we can unravel these things. So what I'm going to do is take the Liouville equation for the reduced system operator, again just for a field mode, and I've got a sandwich term S and the anti-commutator term L minus S. And what I'll do is I'll write it as a sort of Dyson expansion, just a formal expansion. And you'll see that you get a whole sequence of these things. So in this diagrammatic form up here, I've got from t equals 0 to time t, I can evolve under L minus S, or next term in, L minus S to a time there, the sandwich operator, and then L minus S to time t. Or I could do it twice, and so on. And this time is a random time, or any time within that interval. And you do it forever, okay? So that means I can get a whole set of these trajectories, but I'm going to integrate all the random times where that S operated, and then I'm going to sum all these trajectories up. So everything inside those curly brackets is a particular trajectory, where one of these would have occurred. So there's a conditioned density operator conditioned on just one, no jump is what that would turn out to be, and then with a sandwich term that would be a one jump, and so on. Okay. Right. So if I take those conditioned system operators, okay, I can write it in this form because it's pure. Okay, for a single trajectory is a pure state. Okay, so I write it like that. And what happens is that L minus S term in the invariant form propagates your conditioned density operator without a jump. On the other hand, if there is a jump, you have the sandwich term. So for the conditioned pure state component, that sandwich term is just the annihilation operator acting on that, unless you jump. Okay? So if you look at the non-jump term, instead of propagating rho, let's look at the conditioned operator. You just got an effective evolution operator which is non-Hermitian. You've got a little damping term in there. Okay? So you freely evolve with or without jumps. And you could do a Monte Carlo simulation based on all of those things. Okay. So if I look at my Fock state all over again, for a particular evolution, the ensemble is doing that. That's called exponential decay, of course. It's just that it's decaying away at a rate which is omega divided by q. But for a particular realization, you can see what's actually happening is I'm getting these random jumps. The time of that jump is random, and so on. So for this particular realization was a long period here, with not much going on, and then a jump. And if I average over a whole set of these trajectories, I'll get the exponential decay. The timescale for a jump is interesting. So the effective Hamiltonian isn't changing n, but the jump takes you from n to n minus 1 with a probability, which is that, which is the gamma n. Okay. So the decay time for a Fock state is n times the energy decay time. Right. Now let me take a superposition, a Schrödinger cat superposition of the kind that David talks about. So harmonic oscillator, and I'm going to have, this is Schrödinger kitten really. So I've got a lump over there, that's my bits of my superposition, and these are interference fringes that David showed you. But this time, instead of looking at the ensemble, I'll look at one realization. Now as soon as you get a jump, that's the annihilation operator acting on your conditioned state. The annihilation operator acting on this Schrödinger cat state, acting on a coherent state, gives you the coherent state back again. Acting on a coherent state minus alpha, gives you minus alpha again, but with a minus sign in front of it. Okay? So in other words, an even parity Schrödinger cat state that you started with jumps to an odd parity Schrödinger cat state. And you can see that because there's the Schrödinger cat before the first jump, there it is afterwards. The fringes have changed their parity. Okay? So you get a jumping cat, the cat's still alive, bit by bit, but its parity is changing all the time. And if I average over a stochastic set of these things, of course, then the fringes will go away altogether. So if you looked at a particular realization, you'll see a cat jumping from one parity state to the next, stochastically. If you do this for an ensemble of such things, you see the fringes will just disappear. So let's look at it for an ensemble of these things, and that's something I did with Antonio Vidiella Barranco and Vladimir. Here's my cat superposition, fringes in the middle, and this is now for the ensemble. And then an incredibly quick time, which is the distance in phase space squared later, the fringes have gone. Okay? So for the ensemble, cats die. Okay? But for particular realizations of these things, you can see you get a jumping cat. So it depends on how you acquire the information. If I prepare a very large number of these things and let it rip, I'll see something very different from studying time by time the trajectory of a single realization. And of course what we do in core information processing is make single realizations of these things. Okay. So Roche has done experiments on these things. He's made it with his micrometer set up, Schrödinger kitten states with a separation for these things which you can adjust. And what he sees now is exactly the kind of decay behavior I just showed you. Done experimenting. These are pretty small cats, by the way. We're separate. These are ends of 5.5. So the alphas are really small. But what he was able to do is to show how the alpha variation changed the decay behavior. Let's look at spontaneous emission jumps as well, and that was mentioned by David because shelving is the way that you actually do a lot of your manipulation of ions. I take a V system with a strongly allowed transition like so, and a weakly allowed transition, that could be a metastable state. But I get, for a single realization, I can get a lot of fluorescence when I'm doing that, but as soon as I make a transition to this state, the fluorescence will stop. Okay? So, just to show you what happens, this is from Richard Thompson's group from ages ago. You can see this random jumping. So you get a strongly allowed fluorescence interrupted by every time you make the transition to a shelving state. Then you have to wait a certain time before it falls down again and restart the fluorescence. If you took a fluorescence an iron species where the fluorescence is at a visible wavelength, and you darker that, and you look through a microscope lens, you can see the light from a single ion, and you can see it blinking on and off by this sharpening interaction. You can actually see quantum jumps with the naked eye that way. Okay, you couldn't do it with mercury because that's a UV transition. Right. Now I'm going to apply this to a simple quantum information processing situation, which is a quantum walk. So things I did with Kendall. Right. So a cast of millions working with us on this one. What a quantum walk is a quantum version of the drunker's walk along inside space. You know, you can go from here to a lattice distance along to the left or the right stochastically. And these sometimes called QuiCCs, and I'll should explain why. Did anybody know the origin of the word QuiCCs? It was the attack formation for a Roman legion, where you put shields together, you make a pyramid structure on a wedge and you drive it in. And okay, so the first mention of QuiCCs is in Caesar's Gallic Wars. I'm incredibly impressed that the Roman Empire had a website. But if you want to look at the opposition, there's the Asterix website for this thing. And there's a very nice description of how the Gauls coped with the QuiCCs. Okay, right, so quantum walks. Let's look at 1D walks. Okay, so we start from here, and I can go from left to right by steps. So I've got a lattice, and I'll coin toss, and I'll move to the left or the right, depending on whether I get ahead or tail. And I'll repeat it t times. And what I find is the standard deviation for a classical walk, which of course grows with the square root of the number of throws. Okay, so you get a normal distribution, the standard deviation is growing, and the most probable is right at the center. You stay where you are. Okay. Right. So let's look at and the way that these distributions used to be exhibited before computers is you take a pin board. These are pins. You can take the whole raft of marbles up there, and you drop marbles through, and the marbles will bounce off the pin to the left or the right, and end up in bins down here and build up a normal distribution. Certainly, I did that at school. Okay, so that's Galton's QuiCCs, or Galton's board. Okay, so let's have a quantum version where the coin tossing, whether you go to the left or the right, is going to be done with a quantum mechanical coin. Okay? And of course, then a quantum mechanical coin you can put into a superposition of states. Okay, and of course, as soon as you start using superpositions, you can start to see quantum coherences. Right, so what I'll do is a quantum walk. Okay, which is a quantum coin, two-state system, and the flip is a Hadamard, and so I can take a Hadamard, and what I do is I put them in a position X with my Hadamard, then I can go to the right or the left by one step. And of course, if I've been spin up, I'll go one way. If I'm spin down, I'll go the other way. In my superposition of spin up and spin down, I go both ways. Okay, good. Right. Let's let it rip. Okay, so I've got unitary dynamics going on in this thing, and of course my coin, what I'm going to do is choose a whole load of Hadamards to keep flipping it. So I've got to choose an initial condition for this, and I'll flip the coin. Now if I read out the position of the walker after every step, okay, all I'll end up with is a classical walk. So what I'll do is I'll do many steps, and then read it out at the end. And we'll see how the interferences that quantum mechanics will allow through superpositions will allow me to run. Okay, so if I choose a coin flip Hadamard that looks like this, okay, with diagonal elements and off-diagonal elements, and for this particular diagram, this figure, what we've chosen is some particular values of the phases and the distributions up here. You can see what I've done is told the walker to move to the right. Okay? If I'd have changed the relative phases in here, I could have got it moving to the left. None of this looks like a normal distribution. Okay? If I had a Hadamard which is symmetric like that, and I chose an initial state of the coin in a superposition. Okay? So I start with a superposition to start with, and how do I like that? What do I find? Instead of a normal distribution centered on the origin, with a width determined by the square of the number of throws, I find that it's piling up at the edges. And what I haven't shown you is what's going on in here. There's wild oscillations with zeros every other throw. And that's because of the quantum superpositions and interference that are going on in there. So that's a quantum walk. When you got such a very funny probability distribution, you start worrying about whether it makes any sense to have a standard deviation. But if you looked at the standard deviation of this thing, it's now quadratically enhanced. Instead of going as the square root of the number of throws, it's going as the number of throws. Okay? So there's a quadratic speed up of the walk because of these interferences. So those of you who know about Grover's algorithm with the quadratic speed up for database searching, you can do Grover's algorithm posed as a quantum walk. It's the same quadratic speed up. Right. Now, we're in an open environment, so let's put some noise in here. Okay? So I could decohere the coin or the walker. I could start fiddling around with the relative phases, put some randomness in. And one of the most amazing things that you work out from this is, of course, you're going to recover the classical dynamics if you put enormous amounts of noise in. And of course, if I put enormous amounts of noise in, instead of getting this initial distribution piling up at the edges with interferences, I'll get a normal distribution. So you recover the classical world with enormous amounts of noise. Okay? But if you put a little bit of noise in, the system's much more robust than you'd have guessed. The oscillations go away for the same reason that the oscillations went away in my Schrödinger cat superpositions. Okay, that's decoherence of that kind. But the extremities, say, look at the width of that distribution, it's flattened out, but it's still enormously broad. So, in other words, the quadratic speed up is weakly affected by dissipation. And that's one of the surprises for this particular system. In other words, a little bit of noise is enabled to get rid of the disruptive interference that was caused by zeros, but it's still enabling the exploration of the same thing. Now, in a different language, that's what was going on with noise-assisted processes in Martin's transport in the photosynthetic set of receptors. Okay. Right, last thing. If I take a qubit system of the kind that we're interested in empirical, not the ones that David's interested in, ions, but now neutral atoms above wires in an atom chip, okay, which is an atomic version of the ion trap, I've got quite similar problems to worry about that David has to worry about, in that there's surface effects on the internal state of the qubit. In particular, if you have a metal, wires for example, that are steering the cold atoms around, because you've got a finite resistivity, that means you've got dissipation. The fluctuation dissipation theorem tells you that there will be fluctuations of the field, and that will cause you heating and spin flips. So what I'm going to show you some stuff that we did with Ed Hines to match up some of their experiments to see how the lifetime of a hyperfine state for a cold alkali atom above a surface is changed by the presence of the surface at finite temperature. Okay? You get this metal slab, and if you think about normal electromagnetic field fluctuations at a hyperfine spin flip rate, the lifetime of a spontaneous spin flip is about the age of the universe. And what I'm going to show you is that a combination of cavity QED effects, or surface effects, and proximity effects and temperature effects, take that timescale from the age of the universe down to seconds. Okay, so a dramatic change. Right. So there's rubidium 87. This state is trapped. that's trapped, that's not trapped, that's anti-trapped, this is expelled in other words. And so what you do is we can start them in here, and the little bit of radio frequency noise that will take you from there to there will mean it will drive you out of the trap eventually. Okay. So what I'm interested in is the lifetime of that state. Okay, so I'll look at the rotating wave approximation, which is going to be good for this. I've got a single two-level atom. I've got a field that's going to be fluctuating. It's in a cavity. It's a finite temperature. It's close to a metal. I have to work out the relevant Green's function for whatever the geometry is for the guided structure, and I whack it out in a Markov approximation, and I get a golden rule type rate, which is going to be dependent on the Green's function. Okay. So you do all of that stuff. You remember that it's a finite temperature, so you put the finite temperature in, so you've got a mean thermal number in there as well. Okay, and you work out what the total lifetime is for this. Okay, so here's some numerics for what happens matched against some very early results that Ed had. Okay, so the lifetime as a function here of the distance of the cold atom to the surface. Okay, and you can see there's if you model the surface as a slab, that's that. If you model it as a wire, you get that. And you can tell that for that particular experiment, Ed was more slabby than wiry. Please don't tell him I said that. Okay? The other thing that we deduced from this is that we could match what was going on in the experiment with the theory, but only if we said, actually, this thing isn't running at 300 Kelvin, Ed. It must be running at 380 Kelvin. And later checks revealed that that was actually true. Okay? This is a remarkable experiment, by the way. You've got Bose condensed on very cold atoms, a few microns above a thing that's hot in a vacuum system. So what they've actually done, in a sense, is built one of the world's most expensive thermometers. Okay? Now, you can also say, well, let's look at what happens if you have slabs on these things. You can have dielectrics, you can have superconductors, and Steph and I have looked at all of these kinds of things. And what we could do for the slab geometry is we did some calculations, and the Vuletic group gave us some data, and we could match the Vuletic data against our calculations for the slabs as well. But this demonstrates a really severe effect of surface proximity. That the lifetime of a spin flip in free space would be roughly the age of the universe, and it's gone down to a few seconds simply because of cavity QED effects, your proximity to a surface, plus the fact that you've got some thermodynamic thermal noise around. Okay, so that's an extreme version of deep ignorance. So, I thought I'd actually, I've worked in quantum optics now for, a long time. Started in '67. I thought I'd list some of the ways that I've wasted my life, okay, on things that don't matter. Because I thought if I shared them with you, I could at least persuade you not to try them, okay? Here's the first trap that people fell into. I've done all of these, okay? You go back, all the things I've been telling you, and you go beyond the rotating wave function. You put the counter-rotating terms in, but you still think of your atom as a two-level approximation. Okay? That's crap. Because counter-rotating terms are at 2 omega, and there's always another energy level around closer than 2 omega. Okay? So please don't put counter-rotating terms in unless you're doing spin flip microwave transitions, then it works. Okay? The other thing you can do is aimlessly generalizing the James-Cummings model. You know, a 2-photon James-Cummings model, a 3-photon James-Cummings model in funny field states, logarithmic states. I've done all of that. It's pointless. Okay? The other thing to do is to start worrying about strong coupling. In other words, going back to that Born-Markov thing I worried about, the coarse graining, and look at strong coupling for systems that are obeying electric dipole selection rules. Again, it's garbage. Okay? On the other hand, if you want to look at strong coupling in two-level models which are not electric dipole coupled, then there are some things you can do. Then you're into Leggett land. Okay? Another thing that's completely pointless, although I did get 2 Fizerow letters out of it, is to calculate the land shifts, the deltas that I had at one point in the slides, within a two-level model, because it really is just an idealization. But you can waste a lot of time, but if you do that, you'll find that we've already published it. Okay? And the final thing is that a real disease is to worry about non-exponential decay and spontaneous emission. Okay? It ain't important. If you start worrying about what goes on within a range, when you've got a reservoir which is structured, then it is important. But you start worrying about free space. I could keep on going with 3 or 4 more transparencies of how I wasted my life. I've tried all of those. Please don't. Okay? Right. So, to conclude, I stole this from Jacob Dunningham. I guess several of you know Jacob. It's a great cartoon. Dr. Euclid. There is actually a guy called Euclid around as well, we discovered. Who's fired cats through slits and find that they don't interfere. One of these maybe, I don't know if any of you have been following the news of the lion in Essex, but you know, the lion in Essex looks remarkably like one of these cats. Okay, so there we go. But this is the one I like. Thank you very much for listening.
We're a bit late, but we did have a question.
Silly question. For open system, we usually solve it by master addition or by the quantum jump approach. So my question is, what's the relation between the two, or difference between the master addition and the quantum jump?
Well, providing that you're working in the same regime as Bohr-Markov is applying, then the quantum jump analysis looks at a single realization. If you average over many quantum trajectories, you get the same result as you would have done if you solved the master equation for the ensemble. So that one tells you about an ensemble of many identically prepared systems evolving. The other one tells you about the individual realizations. So they're the same thing. There's something much more sophisticated that I didn't talk about, which is if we wanted to infer information from that quantum jump analysis of a single trajectory, we've actually hypothesized that the detection strategy has been a counting strategy of detecting the counts of the excitations in the environment. That's not the only way to do a measurement. I could say that what I want to do is measure a field. The environment, of course, you're radiating out into the environment, it could be a field. And if you measure the field, for example, by homodyne or heterodyne detection, then the disentangling into a trajectory isn't the jump stuff that I showed you, but has a localization characteristic of homodyne or heterodyne. So then you see localization. And then when you go through the appropriate stochastic equations of that, it then locks into a whole range of things that people working in quantum probability already knew about in terms of localization onto eigenstates of the Lindblad operator. And the gentleman at the front here knows infinitely more about it than I do. Okay, so it depends on what your strategy is. I've always assumed in that we're counting excitation, bang, bang, bang. But I could have measured the field, and then we're into this localization stuff that you get from a particular realization. Okay.